Hello everyone and welcome. Today we're going to be looking at a few examples of recursion. So what exactly is recursion? Well, you can think of recursion as basically a function calling itself within the function. Okay, now that's the simplest definition of recursion, but a recursion statement should also have something called a base case. Okay, so right now we're going to look at a recursion function that doesn't have a base case just to illustrate the simplest definition of a recursion function. Inside the main function, we call neverEnd, which is a void function, right? And here we print hi and we call neverEnd again. So if we just think about this logically, if we call neverEnd, we go back to system.out.println hi, and we keep on calling hi and hi and hi until we basically have an infinite loop. So I'm not going to run this because this is going to cause a Stack Overflow error. Because we are literally printing hi forever and forever and forever. You can think of this as like while true, print hi without any break, right? In the same way, we need a base case in order to prevent this from happening. We need a way out. We need an exit ticket from this function. Let's take a look at a simple example to see what I mean by this. Here is a class called fallback, okay? So in a lot of games, we are trying to filter out user input, right? Like let's say in a text adventure game, we ask the user, do you want to go left or right? And if they enter something random like I want to troll you, right? What are you going to do? Are you just going to crash? No. You just ask them the question again, like nothing ever happened, right? How do we do that? We can use recursion. So let's take a look at this, right? Fallback statements are subcategory of recursion statements, are used to ensure that the user inputs all the data correct. So here we print out a lot of fluffy text, and then this is the important part right here. We call real life example, which is our recursive function. Okay, so right here we use a scanner to ask the user some input, right? Which direction do you want to turn, left or right? So these two are called base cases. Okay, so they're called base cases. It's very important that you get that. Okay. The reason why these are called base cases is because this is the way we can exit the infinite loop, right? This is our break statement. Once we reach here, we don't have to call real life example over and over and over again. But let's say they didn't enter left or they didn't enter right. Here we call the recursive statement, right? This is the recursive statement. So when you call real life example, we go all the way back up, we ask the question again. We enter something random again, we ask the question again until we ask left or right. So let's run this and let's see what happens. Okay, so do you want to turn left or right? Okay, I'm going to enter something random, something completely garbage. Now I'm going to say left, and boom, we've exited out of that recursive statement. Now let's look at a more algorithmic recursive statement. Okay, so now let's take a look at this factorial class. Here we are going to be finding the factorial of a number in two different ways. What is a factorial? Well, let's take a look at 7 factorial. 7 factorial equates to 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so you can think of it as this. This is the formula. If we have n factorial, then we basically do n times n minus 1 times n minus 2 times n minus 3 all the way until we reach 1. Okay, so here's a nice little sequence to tell you how that works. Okay, this is an example of something called linear recursion, where each function call only results in one more function call. Okay, so basically we're not branching out, right? Each function call does not call itself 3 more times or 4 more times. It just calls itself 1 more time. We'll take a look at this, but basically what you should know is that any sort of linear recursion can always be modeled by iteration using loops. So I challenge you to pause the video and create a function using iteration to find the factorial of a number. Not recursion yet, right? Okay, so if you've done that or not, let's move on. Here we ask the user for n. We'll find n factorial, enter n, and we find the factorial in 2 different ways, recursive and iterative. And we print out both of their answers. So let's take a look at this program. Okay, we'll find n. Let's enter 4. 4 times 3 times 2 times 1 is 24. Makes sense. Okay, and as you can see, both of them are the same. So let's take a look at the iterative function first. It's a very simple function. Here we have a product which is equal to 1, and we have a for loop with a counter, I. So basically I is equal to 1, then I will be equal to 2, all the way until I is equal to n. So let's say n is equal to 4. So let me write something right here. N is equal to 4. Okay? Or let me close that as well. Okay? So I is equal to 1. We multiply that by 1 and set product equal to that, which is 1. Then I is equal to 2, right? So 2 times 1 is 2. Product is equal to 2. Then I is equal to 3. Product is equal to 2. 2 times 3 is equal to 6. Then product is equal to 6. We multiply that by 4. We get 24. Now we've reached this end case right here, and we return product. Here is something that might help you understand what I just said. Okay, let's take a look at the recursive way of doing it, which in my opinion is much cleaner. Sometimes, actually, in fact, most of the time when you're doing stuff like this, iteration is actually much easier to write. But sometimes recursion is actually much more efficient and cleaner to write than iteration. Okay, and I wouldn't say this is one of those cases, but still, it looks cleaner, even though it's not more efficient. And I won't get into the reasons why. Okay, so here's our base case, right? Like I said, every function needs a base case. This one returns 1, so it does not call itself here. Okay, here is where the recursive statement lies. N, we return n times find factorial recursive n minus 1. Okay, so try to figure this out yourself, how this works. I'm going to be reading a tracing of this function where n is equal to 4. Okay, let's take a look. I'm going to be reading this right here. Let's call find factorial recursive when n is equal to 4. This results in 4 times find factorial 3, right? But find factorial 3 can be decomposed into 3 times find factorial 2. Find factorial 2 can be decomposed into 2 times find factorial 1. Find factorial 1 results in 1, as we can see right here. This in total results in 4 times 3 times 2 times 1, which is equal to 24. Because we reached our base case. Therefore, 4 factorial is equal to 24. You can test this by entering 5 or 7. Try to trace this yourself to figure out how it works. Another challenge that I have for you is to try to solve a recursion problem by creating a recursive function to return the reverse of a string. So if I enter something like calf, it should return this, fiac, or something like that, right? Good luck. There are lots of other recursive problems online that you can try to solve in order to become good at recursion. It is really hard to grasp at first, but I still recommend you to learn this because it's very helpful, especially when working with complicated data structures like trees and graphs and stuff like that. In fact, I'm going to be going over one mini lesson, but you can stop the video right now if you want to, because this is more of an advanced technique used to iterate through complicated data structures. But it's still pretty important. Here, we are going to be learning about binomial recursion using the Fibonacci sequence. Okay? So, this is a more complicated version of recursion in which each call results in 2 more calls. Okay, so let's take a look here. Okay, we have a function f of n, right? And its definition is to return f of n minus 1 plus f of n minus 1. Okay, you might be wondering, why can't I just do 2 times f of n minus 1, right? And then therefore it's a linear recursion. But for the sake of this video, I'm just going to say that we're going to do it this way. Okay, so let's say right here n is equal to 3. Okay, so f of 3 results in f of 2 plus f of 2. each of these f of 2's result in f of 1 plus f of 1 plus f of 1 plus f of 1. So we went from 1 call to 2 calls to 4 calls, and if we had more, we'd have 16 calls, 32 calls, and as you can see, this kind of looks like an exponential function, 2 to the power of n, which is exactly that. If you guys know about the big O notation, this would be O to 2 to the power of n. Okay, if you don't know that, don't worry about that. Just think of it as it takes 2 to the power of n calls instead of just n calls, right? So if n was equal to 4, we'd have 16 calls. But if it was just a normal linear recursion, we just have 4 calls. Okay? So we're going to demonstrate this by looking at the Fibonacci sequence, a sequence found in nature a lot. So it goes like this: 0, 1, 1, 2, 3, 5, 8, 13, 21. And it has a few properties. So the first 2 terms are always 0 and 1. Then the third term is the sum of the second term and the first term, 1 plus 0. The fourth term is the sum of these 2 terms. The fifth term is the sum of these 2 terms. And so on. As you can see, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21, and so on. Let me explain this to you in algorithmic terms. The nth term is found by adding the n minus 1th term and the n minus 2th term together. The starting two numbers of the sequence are always 0 and 1. This seems something like a base case, right? So the first term of the sequence is always 1. So when n is 1, it always should return 0. And when n is 2, it should always return 1. Okay? So let's take a look at this Fibonacci class. Here we ask the user for the nth term, which term you want to find. We read the input, and we basically print it out. Okay, this is the recursive function right here. So we have a base case, 2 base cases in fact. When we're at our second term, we should return 1, and when we're at our first term, we should return 0. This is exactly what I talked about before. But what do we do if it's neither of those? Well, we want to return the term before it and then the second term before it, right? This is how you do so. Okay, try to understand it, try to trace it yourself, and then I'm going to show you how I traced it. Okay, let's take a look at this trace. Let's call find nth term 4. So when n is equal to 4, we're trying to find the fourth term. This splits up into find nth term 3 plus find nth term 2. Oh, this is already a base case, right? This should equal to 1. Find nth term 3 splits up into find nth term 2 plus find nth term 1. Wait, that's another, those two are both our base cases. So all in all, we have 2 times find nth term 2, right? 1 here, 1 here, and 1 here. And we have 1 find nth term 1 right here. Find nth term 1 is 0, so we disregard that. So basically we have 2 times find nth term 2, which is equal to 2. So the fourth term of the Fibonacci sequence is 2. Is that correct? Yes, it is. Thanks for watching. If you have any questions, please feel free to comment down below. This is Recurse. This is our group project for APCSA. Thanks for watching.